Chapter 1 is on vectors, matrices, and linear systems of equations. So let's take a look at 1.1. So basically, we're going to define vectors in Rn, or Euclidean space, as we call it. A lot of this you would have seen, just in algebra when you're talking about R and R2. And then R3, mostly, you probably saw that mostly in Calc 3, or multivariable calc. So this first part I wrote up already. So 1.1 vectors in Euclidean space. So Euclidean space is referring to basically the real number line. I didn't write that one down. R2, which is basically the xy plane, like that. Or R3 is what we mostly did. We mostly spent time studying in multivariable calculus, or Calc 3, fifth semester system. So that's what we call Euclidean space and your different systems. And we're going to extend this to what we call Rn. That'll be next. So this is kind of a recap, slightly different notation that different books use. This book uses the brackets. And we want to start putting subscripts instead of like x, y, z, because we're going to have extended dimension, essentially. So, okay, so write all those up. So this is R2. And we had seen you can use ij, right, for R2. And then I'll put that down here too. So you could use, what was that? Sorry about that. We're just going to keep rolling here. So V, you could have ijk. So that's equal to, this is what we would have seen before, xi plus yj plus zk. And so that would be a three-dimensional case, which we did mostly. You see that mostly in physics as well. So this is how we often use the notation. So we use just subscripts. This was in a lot of calc books use this type of bracket on the side. Or you could say A, and then you have the components. So A1, A2 are the components. And we say that each of those are just real numbers. So the components are made up of real numbers. Okay, so that should all be familiar to you. Then let's get into some definitions. So two vectors are equal. U is equal to V, if and only if U1 is equal to V1 and U2 is equal to V2. So basically, the components are equal. That's the idea. So if components are equal, the vectors are equal. That's by definition, it kind of should make sense. Okay. So next, let's look at addition of vectors. So we'll just stay in R2, although this can be extended to really any dimension. So addition of vectors look like this. And so when you have a U and a V, those will be my U, and this my V. Say that's X and Y. Then you can make basically that parallelogram. We're going to duplicate that, and then I'll make that dotted. All right, so let's do style. Let's change that to like gray or something. There you go. And then this one, same idea. You put in that parallelogram, make that gray, and then that gives you your resultant vector. Okay, so your resultant vector would look like that if you add them up. So this is U plus V, given that this one is U and this one is V. So U plus V, the addition of vectors, pretty straightforward here, is U1 plus V1, comma, U2 plus V2. And again, we're using the brackets in this book. I think most linear algebra books use brackets like this. Okay, zero vector. If I can write. So zero vector would be each component is 0, 0, 0, etc. And we're staying in 2D. So we call this 2D or R2 for now. Scalar multiple. So we let C be in the reals, right? So, and I assume you're going to look up the notation. I'm going to start using a lot more of the math notation, element of, such that, there exists, for all. So make sure you look at the set stuff I did earlier. Then C times V, the vector V, is equal to, you scalar multiple. Well, actually, let me do this real quick here. Let's go and put it in front. So C, I'm going to move this up so I don't keep putting my wrist on that. C times your V1, or V, sorry. Every time it does that, it messes me up. So C times V That's what I meant to do. Okay, basically that gets distributed across. That's essentially, so you multiply C times each one of those components. C1, C times V1, and then C times V2, etc. So if you're given a vector V, like that, then we can duplicate that. And if we do 2V, then of course that's just duplicated same direction. So that's essentially 2V, given that this is V. And then you could do opposite. So negative V would be the opposite direction. Like that. Okay, so that's just a quick recap, I guess, of vectors in 2D. And it's easy to extend that to 3D. So next, what we want to do is extend this to what we say is Rn, or in space. And it's actually a spatial dimension, is what we're considering it. This was done, I forget exactly when it was, but Riemann, as in Riemann sums, I understand, gave a lecture and said, hey, what about doing this in Rn just for fun? And it turns out it has, of course, all kinds of applications in future physics and things like that. Okay, so let's take a look. All right, so let's take a look now at vectors in Rn. This is when it starts to get abstract. This is when it starts to get kind of cool. We're going to let n be a natural number. Okay, so when I say Rn, it's 1, 2, 3, 4, 5. So it isn't like, negative dimension. It's that's what we talk about. So remember naturals, 1, 2, 3, etc. So that's what we are referring to. So we call it in space. So vectors in space are represented by what we call in tuple. So we'll use x. I'll start this off with an x, and then a vector just like before, this guy here. And so we use subscripts. So it's x sub 1, comma, x sub 2, comma, etc., all the way to x sub n. So that would be a vector in space. Okay, so then R n is the set of all n tuples. So we call this an n tuple. Oh, I just said that. Never mind. So R sub n is the set of all n tuples where each component x sub I is a real number. So where each component x sub I is real. So that is, i.e., x sub I is in R1, or just R. So now let's look at some definitions of what we call vector algebra. So this is definition from the book 1.1. Most of it stuff I'll do is from the book, but sometimes I'll throw in other stuff from other books. So follow my notes, follow the book, and you'll be fine. So 1.1, this is vectors or vector algebra in Rn. So it's the same vector algebra you would have seen in R2, R3. Now we're just going to extend it and define it in terms of n tuples. So let's let V, we'll use V and W. Sometimes using U, it's okay, but it's easy to get those confused. So we'll use V and W. So let's let V equal the n tuple V1, comma V2, etc. to Vn. And W, similarly, W1, W2 to Wn. So same dimension, right? You got to be n and n. So it wouldn't make sense to have, fifth dimension and 10th dimension and add. You'd have to basically make this a bunch of zeros to make it the same dimension. So n is what we want. Little r is a real number. So like these are called scalars. Anytime we are in R, the reals, then we call those scalars. Okay. And then let's do addition. Basically just add components just like before, nothing real special here. But we want to go through and define these pretty rigorously at this level. So V plus W is equal to V1 plus W1, V2 plus W2, etc., Vn plus Wn. Subtraction is really just adding opposites, but they throw it in here for some reason. So we'll just define subtraction as well. Just subtract the components, V1 minus W1. And you can see that that's not commutative. V2 plus W2, etc. I said plus there, sorry. Going too fast. Minus, and then minus Wn. Okay, you got the idea there. Scalar multiple, just as you would expect. Now these are defined, right? These are all defined what we have. And then after these definitions, we will come up with the properties. So scalar multiple for R, so R times your V, R times, and then I'll write that out as a vector this time. So that's V1, V2 to Vn. And so that's equal to, you just multiply each component by R, right? Just like before. RV1, RV2, etc. to RVn. And then that's, if that's negative, then it's basically the same as addition. So if you multiply, you don't really need this. I think the book puts it in there for some reason, but really subtraction is just scalar multiple and then addition, because those end up being just real numbers. Okay, and then the zero vector. So zero vector equals just 0 in each component, 0 all the way to 0. And then there are n positions of the 0. All right, theorem 1.1. Sometimes I'll have the theorems ahead of time, or I'll copy it over and give you time to copy. Sometimes I like going through it and writing it out bit by bit, piece by piece, so I can explain it, especially when they're a little shorter. But sometimes I'll have it all ready to go and copy and paste over. But this time, let's write it out. Okay, so it's not that long. So, and I want to describe it as I go. So let U and V, this time I am and W, and W, because we need three vectors, be in Rn, and C and D are scalars, so those are in R. And often the books will say are scalars, but I like to, that's writing more stuff out than needed. So I'll just use this notation to say that they're scalars. Okay, let's run through them. Number one. And it may not follow exactly the order and how they do it in the book. I think I just go 1 through 10, but it's the same stuff. The numbers aren't as important as the concepts. So U plus V is in Rn. So basically we're saying if U and V are in Rn, the sum has to be in Rn. So it stays in the same set when you add them together. That's called the closure property. So basically we're saying that under vector addition, it's closed under addition. We say closed under addition. The idea. Then 2, this is just commutative. And you can see you commute the component, so no big deal here. U plus V is equal to V plus U. And if you look at component-wise, I won't go through all these proofs, but when you add them together, you just change this order, which ends up changing the order of addition, and it's okay because you have commutative property for addition of real numbers. Okay, that's commutative. For addition, I'll just abbreviate. 3 is associative, so U plus V plus W, U plus V plus W. When you add those up, you have to, it's called a binary operation. You can only do 2 at a time. So you either do those first and then those, or vice versa. So that's what we mean by associative. You associate either those, oops, I meant to do that, or these. So either way, that's associative for addition. Okay, 4 is that there's zero vector, so this is basically additive identity. U plus the zero vector is equal to U. And that's basically additive. Can't write tonight. It's Friday night, so additive identity. Still can't write. That's probably why I left it blank in my notes. Okay, there we go. 5. So basically, additive identity is always there's a zero element in the set. And so when you add it to something else, you get the same thing back. That's what we mean by additive identity. It's identically the same thing. This next one, U plus its opposite, negative U, is equal to the zero vector. And that's called an additive inverse. All of this is really analogous to real numbers. All these properties you would have seen as real number properties. is just now they're vectors. Okay, so this basically means that there's an opposite that you get to add to something, anything, and you can get the zero vector. Okay, so 6 is closure under scalar multiple. C times V is a real number, is an Rn. So that's a closure for scalar multiple. Okay, so 7 is a distributive for scalars. So C times U plus V is equal to C times V, C times U, or I guess I did U first, huh? Okay, so C times U plus C times V. I knew I was going to make that look weird. Okay, so that's just distributive. 8, another type of distributive with scalars. C times D times the vector U is equal to C times U plus D times U. Again, another distributive for scalars. 9 is an associative for scalars. CdV. CdV. So again here, you have to decide what to do. So you're going to do those first, or you're going to do those first. It doesn't matter. So this is, you associate the product of the scalars, or you could do a product of this vector first and then the scalars. And then 10 is the 1 times V is equal to V. So that's an identity for scalars. Not really interesting, but that's identity for scalars. You don't need to know like the name necessarily, but you need to know like these are properties that we get to apply. So next we will prove, I think we're going to do 1. No, we do 2. I'm just going to prove commutative. So I want to show you how you look at commutative with the definition of addition. Okay, so there's proofs for all of these you can go through, and I think I assign a few of those. So let's look at the proof. We're going to look at 2. So we're going to first assume this hypothesis. So we're going to say the same thing basically, and I'm just going to paste it because I can. Okay, so we're going to let UV be an R in, and CD and R. Now we actually we don't even need the W, but that's okay. So we have that U is equal to the vector U1 to UN, and those are all reals in the components. And we have that V is the same idea, V1 to Vn. And so when you add those, U plus your V, you're adding just component-wise, right? So it's just basically U1 plus V1, etc., to UN plus Vn. And so within those elements, we can easily say, so these guys, you just commute those. Those are real numbers, so we may commute them under the property of real numbers. So that's V1 plus U1, and you do that for all the terms, Vn plus Un. And then by definition, that's the other addition. That's now your V plus your U. So that's how you would argue it. So that's really by the commutative law of, or property, I guess. It's not really a law. Commutative property of addition of real numbers. So that's what's really happening. It's pretty, I mean, it's pretty straight up, pretty straightforward, right? Normally you just say something like this: since, that's what I have in my notes, since vi u sub I are reals. In other words, we're just pointing out that within the sum, those are real numbers, and then it's basically implied you get the commutative property real numbers. Okay. A few more things here. Let's see. Okay, so we'll go ahead and stop it here, and then we'll do a couple examples: parallel vectors, linear combination, and another property, and that's it. We'll do 2 videos for chapter 1.